Hello everybody, myself Prasanta Mukhopadhyay, faculty member Electrical Engineering Department, Greater Kolkata College of Engineering and Management. So in our electric machine 2 class, in the last class of synchronous machines, we have started a new discussions actually which we have not completed in the last class. So from that once again we'll start the new this topic. So basically the operating characteristics of synchronous machines, and actually this is this characteristics is examined under variable load and variable excitations, and one of these quantities will be assumed to be held constant at a time, while the other will be allowed to vary over a wide range. And also we have assume that since the armature resistance of the machines is very negligible, and we have very low, and that's why we have neglected. And as a result, this does not significantly change the operating characteristics of the machines, but leads to easier understanding of the machines. So by virtue of this negligible resistance assumptions, the electrical power at the machine terminals and mechanical the mechanical power at its shafts are simply related by these equations. This is for generating machines. So input, output, electrical output power should be equal to the net mechanical power input, and for motoring machine, this is the say electrical power input should be equal to the net gross mechanical power developed at the shaft. So actually from this we have come to the discussions of say power angle characteristics of the machines. Basically this is the equivalent circuit of the synchronous machines at generating mode, and this is for motoring mode. From this you can see this equation EF should be equal to Vt plus Ia XS, and since armature resistance are being neglected, and here it will be EF should be equal to Vt minus J Ia XS, that is equal to a synchronous reactance for the motoring mode. And this is a Phasor diagram for generating mode. See, this is actually EF should be equal to this Vt plus J Ia XS, and this is for motoring mode. So if E equal to EF equal to say Vt minus J Ia XS. So this is the Phasor diagram. And see, from this actually we can write this EF by, from this triangle, EF by sine 90 plus minus phi equal to Ia XS by sine delta. From this triangle itself we can conclude. So basically this triangle, this so this OMP, this triangle OMP. So from this triangle, okay. Now we can write this actually equal to Ia. This is actually cos phi. So this is equal to Ia EF by XS sine delta. So if we multiply both sides by the terminal voltage, so it will be Vt Ia cos phi equal to Vt EF XS by sine delta. So this is nothing but the power, electrical power exchanged with the bus bar, and delta is the angle between EF and Vt. So that is shown here. So this is actually power angle or torque angle, whatever it is. So this is called power angle. So actually this is power angle of the machines, and delta has opposite sign for generating and motoring modes. And the relationship of this equation, so that is power angle known as the power angle characteristics, and it is plotted for given Vt and EF, and the maximum power is actually when sine delta is equal to 1, that is 90 degree. So P max equal to Vt EF XS. So that is plotted here. So this is actually maximum power P max, and this is for the generating mode, and this is for the motoring mode. This is for the power angle characteristics. So maximum power occurs at delta equal to 90 degree, beyond which the machines fall out of state, and there is loss of synchronism occurs, and the machine can be taken up to P max only by gradually increasing the load. So this is known as the steady state stability limit of the machines, and the machine is normally operated at delta much less than 90 degree. And the Phasor diagram of generating machines under conditions of Pmax is drawn here. So actually it is Phasor diagram for the generating machines at a steady state stability limit. So here delta is equal to 90 degree. So that actually you can get it from the generating machine. So from this diagram itself, basically if you say plot, yes, it is equal to delta equal to 90 degree. So this will be reduced to that figure. Okay. So operations actually say obviously armature current will be several times larger than the rated machine current in this condition. So that is very dangerous. So operations at constant load with variable excitation. So at constant load, so from this equation 8.42 C, so it is equal to, we can write this, okay, EF sin delta equal to P excess Vt, that is equal to constant. So also Vt Ia cos phi equal to P, this is actually active power, so this is also constant. So Ia cos phi equal to P by Vt, that is constant. So if it is observed, therefore, that at a constant load, as the excitation EMF EF is varied by varying the field current IF, the power angle. So actually, this, if it is varied by varying the field current IF, so basically what will happen? The power angle delta varies, and such that the EF sin delta remains constant, and the machine behavior is depicted by these two figures. So for generating machines and for motoring machines. Okay. So we are coming later on this part. So basically, as EF varies, the tip of the phasor EF moves on a line parallel to Vt, and at a distance EF sin delta equal to P excess by Vt from it. So that is shown here. So as EF varies, so tips moves around a horizontal lines parallel to Vt at a distance of P excess by Vt. Okay. So and since Ia cos phi is constant, the projection of the current phasor on Vt must remain constant. The tip of the current phasor traces a line perpendicular to Vt at a distance Ia cos phi equal to P by Vt. So that is shown here. So this is the tip. This is say a line perpendicular to Vt at a distance of P by Vt. So what we are finding here from this, the current phasor Ia is always located at 90 degree to phasor Ia axis. The phasor joining the tips EF and Vt in the direction of EF. So that is shown. Actually, see, always it is 90 degree. So the excitation EF corresponding to unity power factor is known as the normal excitation. So that is here. This is known as the normal excitation. Okay, and while the excitations are larger than this is called the over excitation. So this is over excitation. Okay, excitation larger than unity normal excitation. So it is over excitation, and less than it is called under excitation. It is called under excitation. Okay, and the conclusions we can draw from this phasor diagram like this, from these figures. So actually, for generating machine, the machine supplies a lagging power factor current when overexcited. So actually, so for generating machine, so it is a lagging power factor current when it is overexcited, and up to this. Okay, and when it is say under excitations, when it is say leading power factor. Okay, and the machine supplies leading power factor current when under excitations. For the motoring machines, at the same time, if it is for the motoring machines, so actually what we are finding the machine draws a leading power factor current when overexcited, and the machine draws a lagging power factor current when underexcited. So that is shown here. So overexcited current machine draws, that is when it is actually overexcited, that is leading power factor, and underexcited, that is lagging power factor. So it is easily observed from these Phasor diagrams that the magnitude of the armature current exhibits a minimum when its excitation is continuously increased from an underexcited state, and the nature of the IA versus excitation IA plot for various values of load, that is real power, is known as, that is shown here in figure 8.33 here. So this is actually shape is like a V, so that's called the V curve. And these are known as the V curves of the synchronous machine by virtue of their shape. And though only one figure is drawn for generating and motoring operation here, so the actual shape of the V curves of the two cases will not be identical, and that will be discussed later on in the elaborately. Little reflection will show that power factor versus IF plots will be say inverted V curves. So that is also shown here. That is inverted V curves. So this is part of the IF. Okay. So actually, what we are getting from this minimum excitation. So from figure these two figures 8.32A and B, this is the minimum excitation. So that is actually this is the minimum excitation, and this minimum excitation says since that excitation is reduced from and the angle delta continuously increases, and the minimum permissible excitation here minimum corresponds to the stability limit, that is delta equal to 90 degree. So you will find here, so at delta equal to 90 degree, okay, Vt versus EF, it is 90 degree. Here also you are saying this is EF and this is Vt, so it is 90 degrees. At delta 90 degree, this minimum excitation is possible. Okay, so EF minimum equal to PE excess by Vt. So minimum field current and the corresponding armature current for a given per unit node at the limit of stability is indicated by the dotted lines here. So this is the stability limit. Okay, so and it is easily seen that this IF curve for PM, that is the mechanical power, are say the inverse of IA versus IF plot, and thus these are inverted V curves. These are inverted V curves. So is having maximum stability, maximum value of unity, say power factor. So that is shown here, 8.33A. Okay, and 8.33 and 8.33A, that is shown here. Okay, so that's how. So it is observed from the in a synchronous machine, the real electrical power exchange with the busbars is controlled by the mechanical shaft power irrespective of excitations, and the excitation on the other hand governs only the power factor of the machine without affecting the real power flow. So for in a generator, if it is desired to feed more real power into the busbars, the throttle must be opened, admitting the more stream into the turbine coupled to the generators, and thereby feeding more mechanical power say into the shaft. And as a consequence, the power angle delta increases, and so does the electrical power output. So however, if it is desired to adjust the machine's power factor, its excitation should be very well within the limit imposed by equation 8.46. So that is and compounding curve. So dotted curves of figure 8.33, that is actually these are the compounding curve. So this is the dotted figure. So basically part of the constant terminal voltage, constant power factor, operations of a synchronous machine. For the generating machines operation, these curves are called compounding machine curves, and these are presented once again in say 8.34 in the field current needed for a Actually, we were discussing about the synchronous machine operations at constant load and variable excitations, and both for generating machine and motoring machine, we are finding that minimum excitations say is will be possible at delta equal to 90 degree, and that should be equal to P excess by Bt. So for both motoring and generating machines, and from that actually we can say this is EF minimum that is equal to P excess by Bt, and minimum field current and corresponding armature current for a given per unit load at the limit of stability. Basically this is the stability is increased by the is shown here, this figure. This is the line, the stability limit. Basically mean this as delta excitation is reduced, delta continuously increases, and the minimum permissible excitation corresponds to stability limits, that is delta equal to 90, that is given by EF minimum equal to P excess by Bt, and that is shown here. So this is the stability limit, and you see this is V curves. So it's a family of curves for synchronous constant load and real power variable excitations. This is armature current versus IF at different per unit load of real power. So this is the under excitation, that is leading power factor for generators and lagging power factor for motoring machines, and this is over excitation, that is for lagging power factor for generating machine, and leading power factor for motoring machines. And so it is seen that is the from that if power factors versus field current curves for fixed mechanical power inverse of a IA versus IF plot, and these are the inverted V curves is having a maximum value of unity power factor that is shown here. So this is the stability limit, 1 per unit load and 0 per unit load. So okay, this is for the leading power factor for generating, and this is for the lagging power factor for generating machines. This is lagging power factor for motoring, and this is leading power factor for motoring. This is the power factor versus IF plot. So this is inverted V curves for the synchronous machines at constant load, real power, and variable excitations. So it is observed that in a synchronous machines the real electrical power exchange with the bus bars is controlled by the mechanical shaft for irrespective of excitation, and the excitation on the other hand governs only the power factor of the machines without affecting the real power flow. And for example, in a generator, if it is desired to feed more real power into the bus bars, the throttle must be opened, admitting more steam into the turbine, that is which is coupled with the generators, and thereby feeding more mechanical power into the shaft. And as you can see, the consequence, the power angle delta increases, and so there is electrical power output. So that is from the earlier equations we have seen. So however, it is not. It is if it is desired to adjust the mechanical machine power factor, so its excitation should be varied well within the limit imposed by this equation 8.46 here. That is we have seen. Okay, these equations. Okay, so actually with this observation we can draw the compounding curve, and this is the in figure 8.33. Basically this is the compounding curve. This is actually here. This is the dotted lines. So it is found that say pertain to a constant terminal voltage, constant power factor operation of a synchronous machine. For a generating machine operation, these curves are called compounding curves, and these are presented once again in figure 8.34. It is here, compounding curves of the synchronous generator. So this is field current, and this is armature current. So this is for 0.8 factor lagging, unity power factor, and 0.8 factor leading. This is the rated load. So as field current needed for a given armature current or KVL loading at a particular power factor for constant terminal voltage. These are useful guidelines for generator operation in a powerhouse. And it is also since that above that a synchronous motor under overexcited condition operates at a leading power factor. So that is we have seen in here also. At leading power factor, synchronous motor operates. See, motor at leading power factors. So we have seen in the earlier diagrams also. So it is operated at a leading power factor, and synchronous motors are therefore employed in large power installations for improving the overall power factor of the installations. And at no load with losses assumed negligible, asynchronous motor operates at delta equal to 0. That is, which means that excitation EMF and the terminal voltage are in phase, and it is seen from the Phasor diagram of this figure. So this is actually EF and VT. This is for under-excited and as inductor, and this is for over-excited as capacitors. Okay, so it's at leading power factor. So the machine's motor draws at 0 power factor leading current. Okay, and this is as a capacitor, so this is as an inductor. So I equal to EF minus VT by axis. EF is larger than VT for overexcited and draws the 0 power factor lagging current, and IA equal to VT minus EF by axis. The EF is less than VT, that is underexcited. Thus, a synchronous motor at no load behaves as a variable condenser or inductor by simply varying its excitation, and the machines operates under such conditions. Motor on no load or light load is known as the synchronous condition, and finds applications in large integrated power systems for improving the power factor under heavy load conditions, and for improving or decreasing the power factor under say light load conditions, thereby controlling the voltage profile of the power system within reasonable limits. So dual purpose synchronous motor, actually synchronous motor is used in industry, factory for serving two purposes. It drives a constant speed mechanical load such as a large power by DC generator, etc., and at the same time it also corrects an otherwise low lagging power factor of the electrical loads such as induction motors and fluorescent tubes, and such a synchronous serving dual purpose and is called dual purpose synchronous motor. So as I told you during the discussions of the breakups, so we will discuss it elaborately what is breakups for a synchronous motor. Basically, breakup is a plot of stator current versus the field current for different constant loads that we have seen, and the graph plotted between the armature current and the field current at no load curve is obtained as the breakups, and the shape of this curve is very likely to the letter V, and thus it is called the breakups of the synchronous motors. And the power factor of the synchronous motor can be controlled by varying the field current IF, as we know that the armature current IA changes with the change in the field current IF. So if we assume the motor is running at no load, and if the field current is increased from this small value, the armature current IA decreases until the armature current becomes minimum, and at this minimum point the motor is operating at unity power factor, and the motor operates at lagging power factor until it reaches up to this point of operation. If now the field current is increased further, the armature current increases, and the motor starts operating as a leading power factor. And the graph drawn between armature current and field current is known as the breakup. And if this procedure is repeated for various increased loads, a family of curves is obtained, and the breakups of synchronous motor is here like this. Oh, this is armature current, this is the field current, this is at no load. So this is actually 0.8 power factor leading region, that is for no load, half load and full load, and this is 0.8 factor lagging, or also this is no load, half load and full load. And leading power factor region, that is it is consumed reactive power, and lagging power factor region say plus Q is consumed. So actually the point and this is the unity locus of the unity power factor loads, and this is the compounding curve. So basically the point at which the unity power factor occurs is at the point where the armature current is minimum, and the curve connecting the lowest points of all the curves for various power levels is called the unity power factor compounding curve. So this is actually the unity power factor compounding curve. So the compounding curves for 0.8 power factor lagging and 0.8 power factor leading are also shown here in this dotted line. And the C of the constant power factor points on the V curves are called the compounding curves. So this is actually the compounding curve. So it also shows is the manner in which the field current should be varied in order to maintain the constant power factor under changing load. Points on the right and the left of the unit power factor correspond to the over excitation and leading current and under excitation and lagging current respectively. V curves are useful for adjusting the field current, increasing field current beyond the level of the minimum armature current results in the leading power factor. Similarly, decreasing the field current below the minimum armature current results in a lagging power factor. So it seems that the field current for unity power factor at full load is more than the field current for unity power factor at no load. So this is the figure between the power factor and the field current at defined loads. So that is at no load, half load and full load. This is the leading power factor region, this is the lagging power factor region, this is power factor, and this is field current. So this is unity power factor. So it is clear from this discussions that if the synchronous motor at full load is operating at unity power factor, then removal of the shaft load causes the motor to operate at a leading power factor. So with this actually will say in a nutshell, we have discussed the operating characteristics, operation at constant load with say variable excitations. We have also discussed the power angle characteristics. We have discussed this V curves, inverted V curves, compounding curves, and when a synchronous motor can be operated as a say condenser or inductors, etc. We have discussed. So everything you will get it. Actually, I have taken this material of discussions based on the books of electric machines by the D.P. Kothari and Nagarath of Tata McGraw-Hill, of course. So you can say help besides this lecture video. You can take the help of any standard books, whether it is P.S. Bimla or it is Nagarath Kothari, or any standard book, even Manvadar or anything else. So each and every book has discussed in details of this for your understanding. And besides that, if you find any problem with this topic, so I am always open to discuss you further. So while you will face any problems, I can help you. So as I told you in previous classes also, everything is given for contacting me, my mobile number, WhatsApp, mail ID, everything. So whenever you will face problem, you can contact me. And what is the main outcome of from this discussions we get? So basically, this is a very say instruction set, or say leading say factors you have to know when you will so work with this synchronous machine, whether it is in a generating station or whether it is in your say future life in the industry. So with this knowledge, so this is not sufficient, but this is a guideline for say how we'll proceed with this machines, etc. What its characteristics, its parameters, its different factors will give you say guiding instructions to deal with these machines for any particular applications or requirement. Okay, thank you all for your say patient hearing. Thank for